Welcome to Study Loop.
Okay, so for this problem, we have a dog running in an open field, and we're given its initial velocity components here. So we know the initial velocity in the x direction is going to be 2.6 meters per second. So that's the Vx here. And the initial velocity of Vy in the y direction is going to be negative 1.8 meters per second. Okay. And we're also given T1, which is the initial time of 10 seconds. And we also know T2, which is the final time, that's going to be 20 seconds. And then it says the average acceleration of the dog has a magnitude of 0.45 meters per second squared. So that's going to be our acceleration then. And we know the dog is accelerating in the direction of 31 degrees from the positive x-axis toward the y-axis. Okay, so our angle theta, which is the direction, is going to be 31.0 degrees. Okay. And in part A, it's asking what are the x, y components of the dog's velocity at the time t2. Okay. So what we're looking for are the x and y components of the final velocity. So I've labeled these vx1 and vy1. Okay. So these are the x and y components of the final velocity. Okay. And in part B, it's asking what is the magnitude and direction of the dog's velocity. Okay. So the magnitude is going to be v1 here, and we also want the direction too. So I'll add a theta here. So the direction is going to be theta. Okay. So I'll call this theta 1 because it's the final direction. Okay. So anytime I have a subscript 1 here, that means the final either velocity or the final direction. Okay. And then part C, it's saying to sketch the vectors for the initial velocity, which is v here, and the final velocity, which is v1. Okay. So again, this vector v is when t equals 1, and the vector v1 is when we have t2. Okay. All right, so let's start with part A then. Okay, so part A, we're trying to find the x, y components of the final velocity. So the first thing we can do is we're given acceleration here. So we can break up the acceleration into x and y components. And we'll see why we're doing that in a minute here. So let's find the x component of acceleration. Well, we know we're given the magnitude of acceleration is 0.45 meters per second squared, and it's in the direction of 31.0 degrees. So to get ax, we do a times cosine of theta, because we're looking at the x direction. So that's why I have cosine theta. Okay, so if we plug in the values for a and theta, we're going to get ax to be 0.39 meters per second squared. Okay, and then to get ay, which is the y component of acceleration, we do a times sine theta, because we're in the y direction now. So I have to use sine theta. So we plug in the values for a and theta again. We are going to get the value of 0.23 meters per second squared. Okay. So now we have A broken up into components here. So now we want to find Vx1 here. Okay. So we know the acceleration is equal to the change in velocity, which is delta V, divided by the change in time, which is delta T. Okay. And let's look at so we're trying to find Vx1 first here. So we're looking at the x component. So I'm going to have an x here. So we have Ax is equal to the change in Vx. Okay. Well, the change in Vx is just going to be the final x component, which is Vx1, minus the initial x component, which is Vx, which we're given the problem. Okay, so we have Vx1 minus Vx. And then this can be divided by change in time. Well, T1 is 10 seconds and T2 is 20 seconds. So the change in time is going to be T2 minus T1. Okay. And now we want to solve for Vx1. So we just rearrange this algebraically to solve for Vx1. Should be a plus here. Okay. And now we can just plug in these values here to solve for Vx1. So we know Vx, it's given to us in the problem. We know Ax, we just calculated that. And we know T2 and T1 from up here. So we plug in those values and we get Vx1, which is the x component of the final velocity. Okay. Now what about Vy1? So Vy1, we do something very similar then. So let's start another page. So now we want the y components. So we have Ay is equal to change in Vy divided by change in T. Okay, so the change in Vy is going to be Vy1 minus Vy. And the change in time is going to be the same. So it's going to be T2 minus T1. Okay. And then again, we'll rearrange algebraically to solve for Vy1. And now we're just putting the values. So we go back here. We know T1 and T2. And we know Vy and Ay. Because we calculated Ay. And we're given Vy from the problem. So we can plug in those numbers. And we'll get the value for Vy1. So I get the value of 0.52 meters per second. So that's going to be the y component of the final velocity. Okay, so that does it for part A. So now part B, we want the magnitude and direction of the dog's final velocity. Okay, so to get the magnitude, we just use the magnitude equation. So we're looking for V1, which is the final velocity's magnitude. So we have Vx1 squared plus Vy1 squared. And then we add those together. So we have Vx1 squared plus Vy1 squared, and then that whole thing is square rooted. So that gives us the magnitude. So now we can plug in our values for Vx1 and Vy1 that we just calculated, and we get the magnitude V1. So I'm going to get 6.48 meters per second. Okay, and then I want the direction. So the direction is going to be the angle theta. So if I want a direction here, theta is going to be inverse tan divided by, or it's inverse tan of the y component of the vector. So our vector is v1, so the y component is going to be vy1, and then that's divided by the x component of the vector. So we're dividing by vx1. So this will give us the direction of the final velocity. Okay, so if I plug in vy1 and vx1 here, I take the arctan of that, I'm going to get 4.6 degrees. Okay, so that gives me the direction. Okay. So now what we want to do is we want to draw these vectors out now. Okay. So let's draw out the one we just calculated here. So this is 4.6 degrees, and this angle is relative to the positive x-axis. So we're going to draw V1 here. So this is positive y. And again, this is part C. And this is positive x. Okay, so vector V1 is going to be here. It's going to be at an angle theta of 4.6 degrees. Okay. And now we're going to draw the initial velocity vector, which is our vector, V here, and that's going to be at an angle of 31.0 degrees. Okay. So now this vector is going to go here. And I'm exaggerating the angle just so I could draw it better. So this is going to be your vector v, and which is the initial velocity vector. And then this theta here, this whole angle here, is going to be 31.0 degrees. Okay. Okay. So we're drawing these two vectors together. This is what we get. So basically, the problem's asking, how do these two vectors differ? Well, they differ in magnitude and also direction here. So if you draw these two vectors here, they're going to be in different directions because the angle theta is different.